So we were trying to find at what rate was the end of his shadow moving when he's 2.5 meters from the post, and we're trying to find the rate of the shadow changing. So we're looking for the distance of the shadow. So we're looking for, we decided this the last time we were together. ds over dt is what we were looking for A, because we're looking for the distance of the shadow, or the length of the distance from the lamppost and length of the shadow. We're looking for this whole thing. And then dy was just simply the length of his shadow, how that was changing. So that was dy over dt. So that's what we said that A and B were both describing. Okay, so here we go. Let me get my head wrapped around this. We know that dx over dt is 2.2 meters per second. That was the only piece of information we were given. And we don't have too much more. What else do we know? We know that this is 4.2. We know this is 1.1. So we got some heights here. But what we don't know is we don't know anything about the lengths. So that's going to be a little bit hard to do because we're trying to deal with that whole S here. We're trying to deal with that whole S. So what I'm going to do is I'm going to do a ratio of side lengths. Okay, we're going to do two different triangles for part A. I'm going to get my handy dandy highlighter out. We're going to look at the big triangle. So we're going to look at the big triangle, and we're going to compare it to, this one never shows up really well, the little triangle. Now, the reason why I'm not using this space in here is this does not make a triangle, right? So the only two triangles I have, and I know they're similar triangles because they both share angle A. They have all congruent angles. When I say congruent, that just means that they're all the same thing. So I'm going to make a ratio about the side lengths. So what I know is that the length of the orange triangle would be equal to y on the short triangle. So I'm putting all like my lengths on the top here. And then we got to compare it to a height. So the height on the big triangle is 4.2, and the height on the little triangle is 1.2. So what I want to do with this is I want to get an equation that's going to have a similar variable. And I hope this is going to make sense in about 2 seconds. I'm going to go ahead and cross multiply and solve for y. And it's going to be in relation to s. So I'm going to have 1.2s is equal to 4.2y. So divide by 4.2, divide by 4.2.
And Ms. Calvin?
Yep.
For the s divided by 4.2, where do we get that equation?
Which equations?
Like this
4. I'm just setting up a ratio because they're similar figures. The orange triangle is a similar figure to the purple triangle in there.
Oh.
So I'm just making a statement about their lengths.
Oh.
And 1.2 divided by 4.2, if I make that into a fraction, if you trust me, it's going to be 2 over 7s. So you're like, okay, that was not really exciting, and I don't know why I had to do that. Well, because we're talking about the lengths of the shadows, and we have really no math, like no numbers for the length of the shadows. We do know, however, that s is equal to x plus y. And what do we know y is equal to?
Y equals to 2 over 7.
So that can go into there. So we're going to have s is equal to x plus 2 over 7s.
Oh, so then we just
Yeah.
solve for x?
Solve for x. And that's a 1 on the S, so that's going to be, is everybody okay if I change it into a fraction of 7 over 7? Just so I can do some quick math. So now we know that x has a length of 5/7 of the whole triangle. We know that that portion, and that y is 2/7 of that. Like if we were to break this down, if we were to look at that, that's 2/7, that's 5/7. Does that make sense? And it works out to be s, which would be 7/7. So we're just kind of breaking down like what the ratio is of the whole thing. All right. So much fun. So we want to take ds over dt. And that is, so that's the derivative, right? The derivative of s. And we know that s has a value of, oops, sorry, that should be a 5. Got my fraction backwards. So we're trying to take the derivative of this function, 5/7 s. And that's what we needed to get it in relation to s, because we were trying to take the derivative of s. Is everybody okay with that? So really, this equation, we know that dx over dt is this. So really what we're going to be doing here is the derivative of ds over dt is going to be our 5/7 times by that derivative.
Wait, where do you get this equation?
The 2.2 is from, it was given in the actual equation.
Yes, but like, how do you know that like 5/7 times ds over dt was equal? Oh,
Because we're doing the derivative of s, right? And we're doing it in relation, the only information we have as a rate is that the rate of the boy running towards the lamppost. So he's running towards the lamppost. So that's the only rate that we have. So maybe this is a better way to write it. ds over dt is going to be the derivative of x. It's going to be the derivative of x, and we know that x is this right here,
yes.
right? So that's where we're getting the 5/7 times by the 2.2. And that's going to be 3.08 meters per second. Okay, do I have more? Hopefully B is a little bit easier. We have the equation, S equals x plus y. We know that from that. So if we take the derivative of all sides, what do we know? We already found the derivative of s, that's 3.08. We were given the dx, which is 2.2, and then we have dy over dt, so then we're just subtracting. So that one's not a lot of math. Not a lot of hard math here. And that's going to be our answer for dy dt. That's probably one of the harder ones to do, just because it's rates and it's different. It's 3 different rates that are happening inside one triangle. All right, we're going to the cone next. You're working backwards. We're going to the cone next. Okay, what you need to know is you need to know the volume of a cone. The formula for volume of a cone is 1/3 pi r squared times by height. That's going to be important. Okay, so it says the radius of a conical, so a cone shake, stalagmite, so that's rising up from a cave floor. What's the other one called? Coming down from the cave roof. Yes. Is always 8% of its height. So the radius is always 8% of its height. And the volume is increasing at a rate of 156 pi centimeters cubed per century. Per century. So every 100 years. What is the rate of change when the radius of the stalagmite is 60 centimeters high? Okay, so we're going to define our variables.
So radius equals to 0.08 times height, right?
Yes, we're going to need that in a second. Let's just define our variable. Okay, let's write that down. So radius is equal to 0.08 of the height. That's what it told us in the equation. So h represents the height in what? Centimeters? What else we got? We got radius. What else do we need to know? What are we trying to find? Time. So we have time in how, what is our time measured in? Centuries. And there's one more thing that we're trying to find. The volume. Okay, that's exciting. What do we know?
Radius equals to 0.08 times height, and volume equals to 1/3.
Okay, so we know that we can replace the r with this expression here in the volume formula. So 1/3 pi times 0.08 h squared times h. And if we actually do the math, and I'm going to leave decimals inside of fractions, which makes me feel a little queasy, but I'm just going to roll with it. And we know one rate. What rate is it that we know? Yeah. We know dV over dt is 156 pi centimeters cubed. Oh, that's supposed to, that's a terrible centimeters cubed, but you get what I, per century. Okay, so we did a whole bunch of math. We did a whole bunch of math that we need. So first thing we're going to do is we are going to differentiate volume. So if we differentiate volume in respects to time, what we're going to be doing is essentially we're taking this equation and we're differentiating both sides of it. So we're going to take the derivative, let me put the t in there, of 0.0064 h cubed. Okay, so we're going to use our laws. I'm going to put that out later. I'm scratching out that dt for right now. dv dt We're going to bring this, ooh, forgot my pi symbol in that. We're going to bring that out front because that is a D3 rule. And we are differentiating H3 in respects to time. So that's going to be dV over dt equals 0.0064 pi divided by 3. And then when we differentiate this using our basic rules, what do we got? 3h squared, right? But that's differentiated in respects to height over time.
Also, it's just basically going to our old rules.
Yeah, we're just going to our old
like
rules.
Y prime.
Yep.
So do Y prime the same as
Okay, so I have a differential here, I have a rate here, and I have a rate here. What do I know from the question? Didn't you tell me we know what dV over dt is? So we're going to substitute that in. Oh, I forgot a 0. I'm going to cram that in there. Okay, can we isolate this? Can we isolate that ratio?
But
I think
we
we can.
Still have an H variable. Right?
That's okay. We're still going to have an H variable, and that's okay. Okay, so we now know the rate that the height is changing, or we know the equation of it. So what do we know? We know that if we go back to the question, I'm just going to slide up for a sec. It wants to know what the rate is when it's 60 centimeters high. So when the rate is 60 centimeters. So we have this fancy formula that we've put in here. So we can go ahead and substitute in that 60 into it. And that's height. So what units of measure would that be? Centimeters per century, right? I didn't leave myself very much room, but you see me cramming that in. It's not, we're dealing with height now, so it's not a cubed. All right, so this didn't answer our question though. Our question's about the rate that the radius is changing. So we had an equation that Rahat was so nice to give us that's related to radius and height, the relationship between them. So if we have that equation, r equals 0.08h, and we differentiate both sides of that, so dr over dt equals 0.08 times dh over dt, because we're differentiating both sides. We know what this is because we just found it. So dr over dt 0.08 times by 6.77. So why couldn't we jump right into, anybody know? Why couldn't we jump right into using that volume formula?
You know, like, why do you have to do a differentiate?
Anybody have an idea why I couldn't use the regular volume formula? It's definitely changing. We had a volume here, which we knew the rate of it. But when I go to differentiate this, I had two different variables. And so with two different variables, it's like solving this equation. If I don't know radius and I don't know height, it doesn't really work. So I had to get this where it only had one variable, and I can get dh, and then I can go back and substitute it in. Because you'd have a dv, a dr, and a dh all in one equation, and you're kind of stymied at that point. You'd have to go to this one, do the differentiation, get a statement about it, then put it back into here. We just did it forward. So you can't have too many unknowns in the equation. So that was why we did it that way. And that, so we got 0.54 centimeters per century. This is my least favorite lesson in the entire course, and you just have to survive it, and we will get through it. And I hope not to put too many running questions on things.